Hi guys, so we're looking at 27.3 Fission and Fusion today. So I want you to be able to describe how much energy is released in a fission or fusion reaction, explain why small nuclei can't be split, and explain why large nuclei can't be fused. Oh, I've got an answer there, sorry, didn't put the animation in. Oh well. So induced fission is where a uranium-23592 or a 23994 plutonium are bombarded with neutrons to make them split into roughly equal parts. And this is what happens in a nuclear power station. Induced means to start. So 23994 Pu is an artificial isotope that's formed by bombarding 23592 uranium with neutrons. So both of those can be used in a nuclear power station as fuel. Now each fission event will produce 2 daughter nuclei and then 2 or 3 fission neutrons depending on what the daughters are. A chain reaction can then occur when the fission neutrons go on to split further nuclei, which you would have learnt about at GCSE. Now, one fission event can produce about 200 mega electron volts of energy, and it's really important you remember that number. So if you had a mole of uranium and you could fission it all, how much energy would you produce? Well, in order to do that, you need to know that 1 mole has got 6.02 times 10 to the 23 nuclei. So if you split every single one, you would find that you would get 6.02 times 10 to the 23 times 200 mega electron volts. And it comes out as about 1.9 times 10 to the 13 joules, which is a huge number. However, it is very difficult to fully fission that much uranium, and so you wouldn't necessarily be getting that much. Okay, so let's have a look. Here's some diagrams to show you the process of fission. You probably saw these at GCSE. So 1 neutron, in this case it's uranium fission, hits the uranium atom, which is already unstable because it has a low binding energy per nucleon, so it will split into 2 daughter nuclei. The 2 daughter nuclei, because they're smaller, have a higher binding energy per nucleon, and in this one case you're getting 3 neutrons. Those neutrons can then go on to produce more fission reactions. So if we look at the diagram here, you've got, let's wait for it, the GIF, you've got a neutron comes in, splits this one's splitting into 2, and they're going on to split 2 more. And you can see very, very quickly that that reaction can become almost uncontrollable. You can see the same thing happening in here, but in more situations. And in fact, in a nuclear reactor, you actually only really want 1 neutron to go on and make 1 other reaction. You don't want to do lots and lots and lots because that is dangerous. We talk about that in the next lesson. So, the energy released. When energy is released in a fission event, it's because the 2 daughter nuclei are positive and they will repel from each other. And those 2, they have enough energy to be able to overcome the strong force and they will repel. And the reason they move in separate directions is to conserve momentum, and their energy takes the form of kinetic energy, okay, which will eventually be heat, okay. Now the daughter nuclei in fission neutrons gain kinetic energy. The 2 daughter nuclei are smaller, they're more tightly bound than the parent nuclei, so they have more binding energy per nucleon than the parent. And the change in the binding energy is equal to the energy released, and that's due to a change in mass, as we've talked about before. So the change in binding energy per nucleon increases from about 7.5 mega electron volts to 8.5 mega electron volts. So remember, binding energy is the energy you need to put in to separate the separate nucleons from a nucleus. So what you're doing is you're releasing about 1 mega electron volt. there. So many fission products are possible when a fission event occurs. Sorry, that's 1 mega electron volt per nucleon, and uranium has 200 and something, 35 nucleons. So that's where we get the 200 mega electron volts from. So many fission products are possible when a fission event occurs. Here's one of the events. You've got 235 uranium. You add that neutron here, and you make barium, krypton, and you release, in this situation, 2 other neutrons, and then you've got your energy release. So the energy released follows Einstein's equation, E equals mc squared. We use Q to denote heat energy in this reaction, but it is E equals mc squared. Okay, and you can work out the mass difference using what you've done before. However, I'll just show you this. So you would add the masses of these two together and then take away the masses of all of these. But because you put 1 neutron in and you get 2 out, there is, in reality, you can cancel one of these neutrons out and you just have the 1 at the end. So the mass number will be mass of 235 minus the mass of 144 minus the mass of 90 minus 1 neutron. If you're in doubt though, and I've done this in the next one, just add this on and then take 2 away. So I've calculated this using these values. So the change, if you want to do it yourself, press pause on the video and the answer's there. But if you want to do it with me, you've got the mass of the uranium here, plus the mass of 1 neutron here, take away the mass of the barium here, krypton here, and then your 2 neutrons here. You can simplify that by just doing the 1 neutron if you understand the above, but if you're not sure, stick them all in. Gives you a change in mass of 0.141 U, and then 1 U is equal to 931.3 mega electron volts, so multiply there. So we're getting 131 mega electron volts in that reaction. Okay, in other reactions you get different amounts. So that was nuclear fission. We go into more about the actual what happens in a nuclear reactor next lesson. But in nuclear fusion, rather than having a large nucleus that has a low binding energy per nucleon splitting into 2 small ones, which is fission, you're on the other side of the graph and you have small nuclei that increase their binding energy per nucleon by getting bigger, okay, up to iron. So fusion is when 2 small nuclei join together to form a large nuclei. When the nuclei combine, they have more binding energy per nucleon and so are more stable. And the energy released is equal to the change in binding energy, exactly the same as fission. Fusion can only occur when 2 small nuclei collide at very high velocity because they're both positive. So you need to force them together. You need to overcome that electrostatic force and get them close enough for the strong force to take over. So they need to overcome electrostatic repulsion in order to get them close enough for the strong force to take effect. So about 3 to 4 femtometers. This happens in the sun. These are the reactions that happen in the sun. It's a 3-stage process. So you have 2 protons, which are basically hydrogen with no electrons. They join together to make heavy hydrogen. Okay. In that process, they release a positron, a neutrino, and that fusion, the difference in mass, leads to an increase in energy of 0.4 mega electron volts being released. You then take this, okay, and you add another proton and you get 3,2 helium, and that leads to about 5.5 mega electron volts being released. So you will need to do this twice to enable you, you need to do this once to enable this to happen, and then you need to do this once to enable this to happen. But in the last stage, you need 2 of these to join together to make helium, and you get 2 protons and then 12.9 mega electron volts. To enable this, to get 2 of these, you've got to do this twice, and then this twice, and then this once. Okay, and this last one, because they're bigger, you get more energy. So, so if you're going to do that twice, you're going to get 2 times 0.4, the first one, and you're going to do the second one twice as well, so 2 times 5.5, and then the last one once to get your hydrogen out. So you get about 24.7 mega electron volts. Now that is less than fission. So if you remember, fission is 200 mega electron volts. So if you get asked a question which produces more energy, per event, fission events produce more energy than fusion. Okay, one's about 24, one's about 200, so almost 10 times more. Okay. However, fusion happens with light elements, and so if you had a kilogram, say, of hydrogen and a kilogram of uranium, hydrogen has a mass of 1 gram per mole. So if you've got a kilogram of it, you have 1,000 moles, okay, which gives you 1,000 times Avogadro's number of atoms to fuse. Whereas if you have a kilogram of uranium, you get about 4 moles because its mass is 235. So you get about just over 4 moles. So you only have 4 times Avogadro's number to fission. So for the same mass of substance, you will have more fusion events than fission events, 1,000 times more. So you will produce more energy from fusion than fission for the same mass of material. I hope that makes sense. Okay. I want you to have a go at the questions. They're here now if you don't have the book, and I will make a video showing you how to do the answers to the questions, and also there's an exam question for you to have a go at, and I'll also make a video for that. Okay, thank you.